Okay, let's continue our discussion of soil deformation, and I rewrote from the last lecture the steps to calculate the settlement of structure. So we're going back through those steps. Number one, find the depth of influence. We have a structure right here, and this structure has a certain width B, and so the stress that's going to increase with depth due to that structure is called the depth of influence ZI. So we first need to estimate how much ZI is, and then once we have estimated ZI, then we'll divide into a number of layers. We then calculate, so we said yesterday that ZI, so this is step one, we said ZI is equal to 4 minus 2B over L times B. So that if I have a square foundation, then ZI is equal to 2B. And if I have a strip foundation, very long one, then ZI is going to be equal to 4B. Right? So that's the zone of influence. Then once I've done this, I can go second step, divide ZI into a number of layers. So if this is the zone of influence, I might divide the zone of influence into a number of layers, and each one of those layers will have a certain thickness H sub I. Step 3, calculate the vertical stress in the center of each layer. So in the center of each layer, I'm going to calculate the vertical stress, sigma prime 0 VI, before anything happens, before I place the load. Then I will calculate the increase in stress due to this loading, and at the same center of that, and that increase in stress will be delta sigma VI. Then I will have to select a stress strain curve, and we'll come back on this. Then I will obtain from the stress strain curve the strain before, that corresponds to the stress before. Then step 7, I'll obtain the strain after, which corresponds to sigma prime OV plus sigma prime V. And then I'll calculate the compression of each layer, as delta H over H is the change in strain. And then I'll calculate the settlement of the structure by simply adding all the compression of the layer to estimate the settlement. These are all the steps. It's a very general method. It works well. The key, though, are ZI, and we discussed it here. And then you can see, so you know how to calculate the vertical effective stress at the center of the layer. You'll do total stress, so gamma Z, minus the pore water pressure or water stress. You've done that before. This is new here, step 4. We need to be able to calculate the increase in stress at depth, delta sigma V at depth Z. So we need to talk about this. Again, we have a structure, and the structure is right here. And the structure imposes a certain pressure P at the ground surface. This pressure P is not constant with depth. It actually decreases with depth, and there is a point at the depth ZI when this pressure P has reduced to something very small. Okay? So we're going to put here the increase in vertical stress at any depth Z. So at the ground surface, we're going to have the value P. The increase in stress at the ground surface is the value of the pressure under the foundation. And then this stress will decrease with depth down to something that's quite small at a depth equal to Z sub I. So the key question then is to be able to find out how much is delta sigma vertical at a certain depth Z. This is Z. We need to find, and there are a number of solutions for this. The 2-to-1 method, Newmark's chart, and I would recommend the bulbs of pressure method, and that's the one that I'm going to discuss with you. The bulb of pressure, so I'm on page 509, and I'm looking at figure 1731. Okay. And this figure looks something like this. I'm going to try to reproduce it so we can discuss it. It has footing, and it's split in half. On one side of the figure, you have a square footing, and on the other side, you have a continuous footing. So this is actually B over 2 of a square footing here, square. And then below the footing, you have a certain number of, the gradation is 1B, 2B, 3B, and so on. And then you have some bulbs of pressure that are shown. We have one bulb of pressure like this, one like that, and so on, and they go deeper and deeper below the footing. Each one of those green lines corresponds to a certain increase in stress, and like the first one, for example, is at 0.9, so this is 0.9 times P. So that would be delta sigma vertical equal 0.9 times P. If I go to the one that's about 1B deep, this one would be delta sigma vertical equals 0.7 times P. So if you know the pressure under the building and you want to know the increase in stress 1B below the square footing, then you will have 0.7 P. You just read the green lines at the right depth, and that way you get the increase in stress at that particular depth. Okay, so this is called bulbs of pressure. And then on the other side, you have another one that's also B over 2, but this one is for a strip footing or a continuous footing, and the lines are different. You'll see different lines. So you have different bulbs of pressure on this side or on that side. So if you need to, if your foundation is square, then you use this side. If the foundation is continuous, you use that side. And if it's in between, then you have to interpolate the two delta sigma V values that you get in that fashion. So that's how we obtain the increase in stress as a function of depth. Because remember, we need that increase in stress at the center of each one of those layers, and using these bulbs of pressure, that's how we get these increase in stress. The next big step, so now we've taken care of 4, we need to look at 5. And 5 is a difficult step. So we need to talk about this, and I'm going to erase this. So so I can discuss that. So stress strain curve. How do we select the stress strain curve? Because remember, what we're going to be using that stress strain curve for is that it's going to say stress right here, and then it's going to say strain right here. And you're going to get a certain stress strain curve. And then it's going to say obtained epsilon B I corresponding to sigma prime OI. So you're going to go here at sigma prime 0 VI, and you're going to read the corresponding value, which will be the strain before the loading takes place in the center of layer I. And then you're going to go to sigma prime VI, OVI plus delta sigma, so I'm going to exaggerate and make a lot of a very heavy structure here, plus delta sigma VI, and corresponding to this, I'm going to find the strain after epsilon AI. And this relative increase in strain is what's going to be equal to delta HI over HI. And that's how, right here, that's how we get the compression of each one of those layers. So that stress strain curve is very important, and it's not easy to select it. I would say I want to make a distinction between two major cases of settlement. The first one is if you have a large building on a relatively uniform compressible soil, then in this case, if you can imagine a certain zone of soil below the building like this, and you're loading that soil zone with this pressure P, you can see that this material is likely to deform by having a certain amount of settlement that takes place under the building, and maybe a bulging on either side of that zone of soil. In this case, that green representation looks like a triaxial test. It looks like a pressure meter test as well, deformation. So I would say in this case, it makes sense to select the triaxial test or the pressure meter test because of the close analogy of deformation. And of course, you would want to look at things that would correspond to the stress level that would be associated with that particular deformation process. But in this case, a stress strain curve associated with a triaxial test, a well-selected triaxial test, and a pressure meter test would make sense to me. If, on the other hand, you're dealing with a fairly thin layer of compressible material under a fairly wide loading, like an embankment, then in this case, so you have the pressure being applied on the soil, you can see that the zone of soil that you're looking at looks more like a consolidation test. It's a fairly thin layer. There's not much lateral squeezing because of the friction that exists top and bottom. So this, it would make sense in this case to use the consolidation test. To use the stress strain curve from the consolidation test. In other words, that black line here, I would pick the triaxial pressure meter for this type of case, like large high-rises in Houston. But in the case of an embankment or over a fairly thin layer of compressible material, then I would think the stress strain curve from the consolidation test would make more sense. Okay, so now we have all the steps covered and we know how to do all this. Let's do an example. So I'm going to, I want to keep that procedure because we're going to be following that procedure. So let me do an example, and for the example, I'm going to page 524. So page 524, right here. And there is a high rise on page 524. So in this case, we have a 180 meter high rise. I want to cut it off right here. And the soil of the high rise is embedded down 15 meters. So an excavation, 15 meter excavation has been dug so that this is 15 meters. And at the bottom of the high rise, then you have a mat foundation right here. And we have, and the high rise weighs 400 meganewton. So the load here is 400 meganewton. The height is 180 meters. So pretty good size, about 60-story building. 180 meters, and the width of the building, it's a square foundation that is 30 meters by 30 meters. Okay. The zone of influence, square foundation, 2B, 30 times 2, 60 meters. So I got to go to 60 meters. Well, it's not going to be to scale because I need enough room to put all the information I want to put in there. So this is going to be 60 meters. And I'm going to divide this 60 meters into 4 layers. So I'm going to put a layer right here, one right here, and then I'll have one here, and then one there. So each one of those layers is 15 meters thick. 15, 15, 15, and 15. And all the calculations I'm going to do are going to be in the center of each layer. Right here, right here, right here, right here. Why? Because if I do calculations in the center, that's going to be representative of what's happening in that particular layer. I need in this case, the solution is going to be based, the stress strain curve is going to be given by the pressure meter test, and therefore I'm going to use elasticity, I'm going to use a modulus, and so I'm going to have a modulus profile given from the pressure meter test. So it's going to be E, and the profile starts at 10 megapascal, so we have megapascal here. We start at a value of 10, 20, 30, and so on, and it increases with depth at a rate governed by an equation which says E equal 10 plus 0.5 Z. So E in megapascal, E megapascal equals 10 plus 0.5 Z in meters. Okay, so that's the equation that gives me E. So that way I can get E anywhere I want, including the points in the center of each layer. So I now have the problem set up, and I'm going to do a spreadsheet. I want to put these layers like this, like this, like that, and like that. And in that table, I'm going to put the layer thickness, H, in meters. And then I'm going to put, what else do I put? I'm going to put the effective stress. Let's simplify the case so that there is no water. So no water. Okay, it's a big dry zone. The soil has a unit weight. I forgot about this. The zone is unit weight of 20. No water. Gamma total equals 20 kilonewton per cubic meter. So no water means that the total stress is equal to the effective stress. To simplify the calculation. So here I'm going to calculate sigma prime 0 V, and that's going to be in kilopascal. The next column, I'm going to get the value of E in kilopascal. And the next column, I'm going to calculate the value of the increase in stress, sigma vertical increase in kPa. And then I'm going to need the strain, the increase in strain, the delta epsilon that I was talking about earlier. So I won't have any units in there, it's a strain. And then I'm going to calculate the delta HI in each layer. So all these are the values. So I'm going to extend the table to go all the way here, like that. Then I get this, then I get that, and then I get this. And then these will be the compressions of each one of the layers, and I'll add those compression to get the settlement right here by adding those. And I'll do delta HI, I'll try to do millimeters here so that it's a more reasonable numbers rather than dragging some zeros. All right, so HI is 15 meters, each layer, 15, 15, 15, 15. Then we have to calculate the effective stress at the center of each layer. And we take the center because that's representative of the average of what's happening in the layer. So the first depth will be 15 plus half of 15, 7.5. So it's going to be 22.5. 22.5 times 20, that's going to be 450. So the stress in the center of the first layer is going to be 450 kilopascal. Then we go to the center of the second layer, and we have 15 plus 15 plus 7.5, so that's 37.5 times 20, and that's going to be 750. And we continue for the center of this layer, center of that layer. Same calculations, that's 1050 and 1350. Then we have to calculate the modulus at the center of each layer. We have this equation for the modulus. So we go back in the center of the first layer, and the depth is 15 plus 7.5, 22.5. So 1/2 of 22.5 plus 10, and that gave me 25,250. Because this is megapascal, but I need it in kilopascal here to be consistent. So 21,250. And then I go to the center of the second layer. So again, 30 plus 7.5, 37.5 times 0.5 plus 10, and that gives you a modulus of 28,750. And so on, as I go down the modulus profile, 31,250, let's see, no, that's 36,250 in here, and 43,750. Let me check something else. Yes. Now we have to calculate the increase in stress at the center of each layer. And that's where we have to use the bulb pressure. I mean, we can use a number of methods, but the bulb pressure is a very convenient method. So the foundation is square, 30 by 30, and to enter the bulb pressure, and you know, I mentioned the bulb pressure, so this is square, so we're going to be on the right-hand side of that figure. Note that there's actually a scale on the left of that figure for square foundations and a scale depth for the strip footings on the right-hand side. So we would choose the left-hand side because this is a square foundation. And then the first depth below the foundation would be 7.5 divided by 30. So that would be 0.25 B, the 1/4 of B. So on the left side of the bulb pressure, I would go down to 0.25 B. I would read across under the center of the foundation, and that would give me the actual number that I would have to use to multiply by the pressure under the building, and that would give me the increase in stress. So I did that, and that gave me 378. This number was 378 using the bulb pressure. And then I would repeat the same thing, but now the depth would below the foundation would be 15 plus 7.5, or 22.5, and 22.5 divided by 30 is 0.75 B. So on this left scale of the bulbs of pressure, I would go to 0.75 B, go to the center, right under the center of the square footing, and read the fraction of P, the pressure under the building that this would represent, and times the pressure that gave me 222. So remember, the pressure under the building is going to be P equals 400,000 kilonewton divided by 30 times 30. So this is going to be, let's see, I have my calculator here. So we have 400,000 divided by 30 divided by 30 equal, we're at 444.4. 444.4 kilopascal. You can see that it's decreased slightly under the center of the first layer and more down as we go. And so if I continue to do that for the other layers, I get 111 here, and then I get 67 in the middle of the last layer. So then I have to calculate the change in strain in the middle of each layer. So the change in strain is going to be delta epsilon, and delta epsilon is delta sigma over E. So I put some I for each layer. And this is a simplification because remember earlier in the course I said the modulus is not directly related to the change in that particular normal stress, but there is an effect of the confinement. We're neglecting this effect in this particular case to simplify the process. So delta sigma I is going to be right here, EI is going to be right there, so delta epsilon is going to be 378 divided by 21,250. So if I do that, I got 378 divided by 21,250 equal 0.0178. This number here is 0.0178. And I do the same, 222 divided by 28,750, and that gives me 0.0077. And again, 111 divided by 36,250, and that gives me 0.0031. And then the last number is 67 divided by 43,750, and I get 0.0015. So these are the delta epsilon. Then the compression of each layer will simply be delta epsilon. So we'll write this here. The compression of each layer, delta HI, will be equal to delta epsilon I times HI. So HI was 15, so we'll do it in millimeters here because the numbers would be too small. So then I have to do 15,000 times 0.0178, and I get 267 as the compression of the first layer. 267 millimeters, about that much. And then I do 0.077 times 15,000, and that gave me 115. Then 0.0031 times 15,000, that gave me 47. And then the last one, 0.0015 times 15,000, that gave me 22 millimeters. So that's the compression of each one of the layers. The top one compresses a lot because the stress is high, and less and so on. And then the total, the movement of the building, the downward movement of the building, the settlement, will be the addition of all those numbers. And when I add that column, then I get down to 451 millimeters. Special case of a thin layer for the consolidation case that I mentioned. Let me take this out and do the special case of a thin layer. And we're going to use the consolidation curve. So remember, the consolidation curve looks something like this. And like that. This is sigma prime on the log curve, and this is the void ratio. And the curve looks something like this. We'll simplify it. Right here we have the important value of sigma prime P, the pre-consolidation pressure. On this side we have the compression index. Right here we have the recompression index. And then the issue is that the effective stress in the material before loading could be either on this side or on that side and so on. So that's what we're going to have to be careful with. But let's say that we have a problem where we have an embankment here, an embankment that creates a certain amount of pressure on the ground surface, and then we have a fairly thin layer of compressible material, let's say clay, and the water level might be quite high, so the clay is saturated. This could be an embankment or a tank, on the Gulf Coast. And the layer has a certain thickness that we'll call H. This case, we will do the calculations again in the center of the layer, call that point A. And there are several cases that we need to consider. The first one is if sigma, let's see, let me actually reproduce it. The issue is we have, so remember that if sigma prime OV is here, then the material is over-consolidated because sigma prime P is larger than sigma prime OV. If sigma prime OV is here, then the material is normally consolidated, okay? And these are the two distinctions that we make depending on where sigma prime OV is located. We're trying to calculate the settlement of this structure, of this embankment. So we need to write down that the settlement, we'll call it delta H, is equal to delta H, C sub C, and so on. So there's an equation that does that, but there are several cases. And I'm going to deal first with the simplest case, where the material is normally consolidated, okay? In the case where the material is normally consolidated, this curve looks like this, log sigma prime E, and we're in this case normally consolidated, so sigma prime OV is equal to sigma prime P. The curve actually starts right here. So this line is actually one single line, and the pressure right here is sigma prime 0V. There is no pre-consolidation pressure, or if you wish to see, the pre-consolidation pressure is equal to the vertical effective stress in the center of the layer. And then right here we have sigma prime OV plus delta sigma V. So it's right there. And remember the slope here is C sub C. And so in this case, the equation for the compression of that layer simplifies to delta H equals H0 over 1 plus E0 times C sub C log of the delta of the log Therefore, the ratio, the log of the ratio, sigma prime 0v plus delta sigma OV, delta sigma vertical, not OV, right here, delta sigma vertical divided by sigma prime OV, okay? That's the equation in this case. And then we have another case if the material is over-consolidated. If the material is over-consolidated, then the curve looks like this. We have void ratio here, and we have log of sigma prime. But the curve has two parts prior to the pre-consolidation value, and I exaggerate a little bit the knee there, and then right here is the pre-consolidation value, sigma prime p. If we have sigma prime, so here's sigma prime OV, because we have a over-consolidated material, and then you're going to have a certain increase in stress. So if sigma prime OV plus delta sigma prime V is less than sigma prime P, that means that sigma prime OV plus sigma prime V is less than this, so we're still on this, then the equation is delta H is equal to H0 over 1 plus E0 times C sub R this time, because we're right here on the C sub R. C sub R log of sigma prime OV plus delta sigma V divided by sigma prime OV. If, however, sigma prime OV plus delta sigma prime V is more than sigma prime P, then that means that sigma prime OV is here. So the first case was we were right there, but the second case we're right here. And this is sigma prime OV plus delta sigma vertical. So in this case, we've got to do two parts for the calculation. And this is C sub C. So we're going to do one part from sigma prime OV to sigma prime P, and then one part from sigma prime P to sigma prime OV plus delta sigma. Okay? So the equation in this case is going to be delta H equal H0 over 1 plus E0. That part is common. But then I got to do the first part of the compression up to sigma prime P. So I'm going to write, and the slope is C sub R. So this is going to be C sub R log of the last one, sigma prime P divided by sigma prime OV, plus the second part, C sub C, because the slope has changed, times log of sigma prime OV plus delta sigma V divided by sigma prime P, because that's where I start that curve right there. Okay? So you essentially have three major cases. You have this case, which is normally consolidated. We have this case, which is over-consolidated, but we keep the increase in stress below the pre-consolidation pressure, or this third case, where it is over-consolidated, but we go beyond the pre-consolidation pressure into the virgin behavior. So that's, some examples of compression calculations. When it comes to the to the consolidation theory, there are two parts. This part is what I would call the magnitude calculations. So this is calculations of, all this is calculations of magnitude of the settlement or compression. All that discussion that we just did, and that's the technique. The other part of the consolidation theory is to estimate the amount of time that it takes for the settlement to take place. Because as I explained in a previous lecture, when you load these materials such as clay that are full of water, saturated, when you load the material, the water has a hard time getting out immediately out of the pores, and so it takes time for that water to get out, and as the water gets out of the pores, the settlement takes place. So the settlement is directly tied to the drainage of the water from out of the pores between the particles. And Terzaghi developed a solution for this other part. So the other part is time, rate of settlement. So let me say a few things about that, and then we'll stop. So time to reach U% of final settlement. My blue pen is running out of ink. That's a different topic, and we won't have time to derive the equation that leads to the solution, but the solution is presented this way. The time required for a certain amount of percentage of settlement to take place is equal to the time factor associated with that percentage times h squared over c sub v. Okay? And the parameters, so t is the time for U% of final settlement, or maximum settlement, let's call it maximum settlement, of maximum settlement to occur. Capital T is the time factor for U% consolidation. Same thing. And basically, this T, this time factor, is the solution to the differential equation. C sub v is the coefficient of consolidation. So you've got to be careful because there are a number of coefficients associated with the consolidation. Right here I told you about C sub C, compression index. We talked about C sub R, recompression index. Now we're talking about the coefficient of consolidation, C sub V. That's a lot of C's, and you're probably going to get this on the final. in terms of the short question. What is C sub V, or what is C sub R? And so these three things need to be kept distinct. And then H is the drainage length. Drainage length. So time factor has no units. This is in unit of seconds, if you wish, or hours, or whatever. C sub V is going to be in units of length squared, so meter square per second. And then drainage length is going to be in meters. And when it comes to the drainage length, we distinguish two special cases. The first one is called one-way drainage, and the second one is called two-way drainage. So here is one-way drainage. So in this case, I have a layer, the same case I was talking about. And then you have an embankment, and then a thin layer of compressible material full of water. So this is squeezing, and then drainage takes place. This is a fill, so water can actually come through the fill, but this is impervious. In this case, the drainage length H, I should put HD here for drainage length so that we don't confuse it with the thickness of the layer. And so H sub D here. And this is the thickness of the layer, H. So in this case, the water that's stuck at the bottom here cannot go down. That has to go all the way up to drain out. And in this case, the drainage length is equal to the thickness, we'll call it H0 to be clear. And then the other case is two-way drainage. Two-way drainage. And in this case, so same picture. And then we have the embankment. This is not the only case, it just happens to be an example. And here is the fill, so the water can drain into the fill. But this may be sand in here. So in this case, you can see that the water that's in the center can drain down or up. Right here it goes up, right here it goes down. So the length of the drainage is equal to 1/2 of H0. So here I have H0, and in this case, the drainage length, HD, is equal to H0 divided by 2. Okay? So this is important, but the expression is quite simple. Just be careful with the units of the coefficient of consolidation, and be careful also about this distinction. Ask yourself, can the water drain top and bottom, or can it drain only one side? It has to be able to drain one side, because if you cannot drain at all, then it's not going to settle. So ask yourself that question, answer that, go in there, and then you can calculate the time. So we'll stop right here, and the next lecture we'll practice with an example.